Now, today's plan is to finish three-dimensional kinematics. I know I introduced three different cases. In fact, there's a fourth one, which of course is less applicable to civil engineering problems, but is more relevant for mechanical applications. I will finish that one because I noticed that I actually provided on my lecture note. And this was actually on my notes, page 59. However, I use a different symbol. I just want to clarify that one. And so that's going to be example 32. And example 33 will be the relationship between moments of inertia and products of inertia. That is example 33. Three-dimensional kinematics. And in three-dimensional kinematics, you know that from the first case, I talked about this was last week, I'm sorry, on Wednesday. So what's the first case? First case is suppose you have a plate, so make it smaller, like this. X, Y, Z. You have 2 points, point A and point B, right? And we said that if point A is moving at the center, of course, center of gravity with a VA and AA. What is the velocity at B and A? Of course, in this case, there's an angular motion. So this is the simplest case. Case 2 and 3, I will not bore you. I just show you the configuration that we did before. A, B. So what did I do in case B? How is that different? You have one acceleration and velocity at A, as well as an angular velocity and acceleration of this object, right? So you also have omega and alpha. That's case 2, right? And case 3 is what? Case 3 is we consider 2 different kind of rotations. You have rotations, velocities at A, VA, AA. Of course, everything is X, Y, Z. X, Y, Z, point A, point B. And what's the difference between these two is we said there's going to be omega 1 and omega 2, right? And of course, you can also define alpha 1 and alpha 2, right? And we were interested in the motion at what? At point B. So that was the summary on Wednesday. What's the motion at point B? We're always interested in B. Now, the fourth case, of course, is what I said. This is more relevant to mechanical applications. Is suppose we still consider this plate like this. And suppose you still have this A. Suppose A only also carries a velocity VA and linear acceleration AA. Now, this point B here, this point B somehow is allowed to move away from point A. Of course, that does not apply to civil engineering structures because we don't have this kind of structures. Once you build a bridge, the bridge will preserve its own shape. Even you consider what we call movable bridge, that will still not be the case. A movable bridge is actually the bridge can actually swing, or it actually can be lifted up or down. But even in that case, each component will not separate from each other. This kind of device is usually we call it robots or robotic system. So that's not really in the case for civil engineers to consider. But for mechanical engineers, this is very, very possible. You have the mechanical system like your vehicles, your engine, they always have this kind of structure. You have device actually like a piston, right? The whole system is one piece, but one component could be actually moving with respect to the other. And that's why in this case, let's consider that this point B can actually move. And this is on my notes, page 59. So suppose we consider that from B to A, there's actually a velocity. So here, because B to A, that means here. In all of this, B and A, there's no relative velocity. That means B will not move. Whenever A moves, B will move along. But in this case, there's a relative velocity which is called VA. Correct? Because relative. So that means point B can actually move with respect to point A. So we're going to say that there's going to be a relative linear velocity from B to A. There's always going to be a relative linear acceleration from B to A. Okay? Now, what's the formulation? The formulation is, we don't have to consider these two, we just consider one first. So let's say that there's an omega here, acceleration here. Now, we want to know, suppose you have this, now with these two, how do you find out the linear velocity and linear acceleration at point B? So that's what I put on my notes, page 59. And I changed the symbols, but I just want to clarify here. This is on my notes, page 59. So how do we find out the information at point B? So this is the final result. The velocity of B, linear velocity at point B, equals to the linear velocity at A plus this angular velocity omega cross the distance between B and A, RBA, and plus the relative velocity from B to A. So here there's the third term. This is D. Now, if you compare this expression with the one I gave you for this case, you can see the difference. This is B. That's for linear velocity. For linear acceleration, and it looks like this. With the linear acceleration at point A, because this graph indicates the center of a local reference frame or coordinate system, plus what? Plus alpha, which is the angular acceleration, cross the distance from B to A. And everything here is still copied from before, on that case, case 2. And then the next one is plus omega cross omega cross RBA. Until here, until this point, this is what I gave you from which case? From case 2, right? You should have the notes from Wednesday. Just put the notes on Wednesday on the side, and you can just compare the difference. Now the following is going to be the difference. So after that, next, the following part is different. First of all, we're going to have this. We're going to have 2 times omega cross the linear velocity, which is VA. Omega cross this one. and plus, but it's the linear relative acceleration from point B to point A.
Quick question.
Yes.
What's the order of operations with the 2 times omega? Is it 2 times omega all across VBA?
Yes.
Or is it? It is. Okay.
Yeah, just 2 times omega. So you can just take this one. It's just 2 times.